Good morning, everyone. Good to see your faces again. How are you doing? Okay? Just waiting for some audio input.
Good.
Yes? Cool. It's an early morning. It's raining outside. It looks miserable, but at least we have statistics, right? Okay, here we go. For today, we will start with the ANCOVA. So I told you before that, for the most part in this block, we'll be focusing on the different variants of the ANOVA. So we've discussed the one-way independent ANOVA, and I told you it's a bit of the same as we covered last year. We've expanded upon that. And we're gonna keep expanding on that topic because, as you can imagine, that the research there has to be a fit between the research design that you have and the statistical analysis that you want to perform. So one of the things that we've been covering in the previous block and also last year. Is the t-tests and this one-way ANOVA, but you also know that when doing experimental research, you want to have some control group, or you want to have you want to apply some treatment, and you want to know if there's an effect of the treatment. So if you want all those considerations taken into account with your analysis, that means that just a simple t-test will not suffice, and you have to expand on that. So for the most part in this block, we will be looking at the different variants of analysis of variance. So it's a very versatile tool to use, and it can be expanded upon quite easily based on the same concepts. So where we last week looked at the one-way ANOVA, so that it's a specific one-way ANOVA. It's the one-way independent ANOVA that we looked at, and we that ANOVA variant had the ability to look at different independent groups if you have two or more independent groups. And you can imagine that sometimes you don't have independent groups, or you have some treatments that you have performed and you want to have repeated measures. So you have to have some more a more versatile toolkit to go about and to make sure that your statistical analysis actually fit your research designs. So today we will be going into the ANCOVA. It's the analysis. It's a play on the analysis of variance, but it's this time called the analysis of covariance. So that means that we actually apply a covariate into the analysis, and we'll dive into what that exactly means. And I also want my pointer to show up. Yeah, here we go. So so the ANOVA is essential. Of the ANCOVA is essentially a slight extension on the independent ANOVA that we performed last week. But with the ANCOVA, you let's say you correct for some covariate. So there might be some variable that you know that exists that could influence the outcome of your results. And if you want to correct for that influence, then you can add this extra variable to control for that. So you actually want to determine what the effect is of your independent variable on your dependent variable controlling for your covariate. So, and this is essentially what the ANCOVA does. I've written it down here again, where you're statistically controlling for that effect. And one of the things that you have to recognize is the way this works is that within the ANCOVA design, as we apply it in SPSS, that covariate, as I will cover today, is a continuous variable. So we have essentially one independent variable, just like we had last week. We have one or more independent variables that could have two or more levels. And I'm stating this quite explicitly here, that you can have one or more independent variables, but we haven't covered more independent variables yet. So we'll be going into this tomorrow in the lecture. But for today, I'll do this example based on only one independent variable and adding only one covariate. And as you see, it's also possible to apply more covariates into your analysis. So the thing is that you have to think about what is actually meant by this covariate, and the fact that it's controlling for your for the effect of the covariate. And you can put it in more in a research design setting, where you know that there are some variable biasing your view on the thing you want to measure. And if you know that such a variable exists, then you can apply this. So it's essentially a confounding variable that you have to correct for. And if you know this exists, the ANCOVA is the way to go and to correct this. And what it is in essence does is it expands your model. So in terms of model, we looked at the model last week, where our model was just the predictions of our independent variable. Those were the expected values that we thought would determine or actually determine the expected values, and that was the model prediction. And by adding a covariate, you're not only looking at the model prediction of your one independent variable, but you're also adding this extra continuous variable to have a model that comprises of both. And therefore, at least that's what we want, therefore reduce the amount of error that we have in our model. So where we last week split the explained variance part and the unexplained variance part, the notion here is that if we add a covariant, we add explained variance, and we therefore shrink the amount of unexplained variance. But we'll go into that into more detail during this lecture. Does that make sense for now?
Yes.
Yes?
Yes.
Very good. Okay, so we have to think about a few assumptions, and maybe I'll look into the example first, and then we'll think about what that implies for the assumptions. So we could have, for example, we want to measure extraversion on extraversie in Dutch. For Dutch people, for German people, and for Belgian people, and we want to know if there's a difference in the amount of extraversion on one of the big five scales. But we might think that this extraversion is confounded or influenced by one of the other big five traits, namely the openness to experience. So we would like to know if there's a difference between the nationalities of these three categories to extraversion, while correcting for the openness to experience. So that is the goal, to instead of having a clouded view on what is going on, now we take that thing where we think, well, this might confound our results, and then we correct for it. So this is something to think about in terms of if it's actually something that confounds and you don't take it into the model, it's still there, right? So if there's a variable that clouds that influences your results, your scores on the dependent variable, then if you don't take it into account, it's still there. But then you think that the actual scores of your dependent variable represent only the dependent variable, and that could yield results that are not actually related to your dependent variable because it's caused by some confounding variable. So only if you take it into the model, then you will be able to correct for it and see what the actual results are only on that dependent variable. So going back to the assumptions, because essentially the assumptions that we have for the ANCOVA are the same as we have for the ANOVA, but there are two additions, and the first one is that the independence of the covariate and the treatment effect. So the treatment effect would be the independent variable. So the categories that you created, in this case being either Belgian, Dutch, or German. And it means that on those categories, there must not be a difference on the within the categories on the covariate. So that essentially means that the levels between the categories on the covariate should be equal. And this is a bit in line with the notion that you want your covariates to have an impact on your results, or at least let's rephrase this. You want to take the impact of your covariate out of your results, out of your dependent variable, but the impact that the covariate has should be equal across all categories. So that is the assumption of the covariate. It can't work. It can't have a bigger effect on one of the categories and not on the others, because if you're going that route, you would not. You should not do a covariance analysis, but you should either go for add an interaction to your term and add the covariate as an interaction term. But okay, we'll not go into that. So the assumption is it should have the same effect on all the three, in this case the three groups. So that means that if you want to test that, you can just apply a regular old independent one-way ANOVA where you use the covariate as your output, as your outcome variable, and there should be no difference. So that is one assumption that should hold here. And the other assumption is a bit in line with the notion that the covariate should have the same effect on all three categories, but it's related to the relation between the covariate and your dependent variable. So, for example, if you take this example that we have the openness to experience, and we have the extroversion trait. So if those two if there's a relation between those two, for example, the higher your score on, let's say, the higher your trait on openness to experience, the higher your extroversion level. So that would be a positive relation. That is the slope that we're talking about. So if we're saying that the relation between the covariates and the outcome variable has a relation, you can see it in the slope of the regression line between those two. The higher your openness to experience, the higher your extraversion level. But what is added is that relation that you have there should be equal across all groups. So the relation between openness to experience and extraversion for the Dutch people should be exactly the same as for the German people, as for the Belgian people. So it essentially states that the covariate has the same effect in all groups. So it would be violated, for example, if there's a positive relation for the Dutch and the German people, but for the Belgian people, the higher your openness to experience, the lower your extraversion level would be. Well, that would be a clear violation of this assumption. Does that make sense?
Yes.
Very good. And there are two ways to actually look at this. Was there a question?
Yeah, sorry.
Go ahead.
I have a question. If the covariance has the equal correlation in all the three groups, is the conclusion later on that we have from the data more, I don't know, let's say Belgian people are the most open to experience, therefore the most extroverted? I mean, like we were asking in the hypothesis, whether there's an influence of on extroversion within these groups.
Yeah.
And if there is, but it's all due to the fact that also Belgian people are the most open to new experiences.
Yeah. I that's a good point, but it's a violation for the assumption of doing ANCOVA. Because the ANCOVA states, or at least the way that model works, requires that there's no interaction between these two, because your regression model does not contain the interaction term. So if that is your hypothesis, and maybe even if that is something that is actually going on, the ANCOVA is not the analysis to perform. You have to go to a regression model where you, for example, explicitly state the interaction term and also add that. So later on in the course, we will be also looking at the moderation analysis, where you actually have a regression model where you explicitly add the interaction term, and in that sense, then there could be a difference between those groups, and you can test what that difference exactly is. But for the ANCOVA, it's a check. So we use the interaction test to check if this is the case. So if you let's say if your assumptions hold, and only if your assumption holds, then it's allowed to perform the ANCOVA.
Okay, yeah, I understand. Thank you, yeah.
Okay, so we have the Dutch, the German, and the Belgian people. And what I'm going to do here is I'm going to simulate some data. And I'm going to simulate it. I'm going to run through it just a little bit so you know what's going on here. And the reason I'm doing that is because I want you to see what we actually put into this. So when we are looking at the results and the analysis finally, then we can compare it to what we actually put into the data, to see if how it relates to each other and where we see the differences, because we're going to see differences. So what I'm going to do here is we're going to have 20 people. We have two groups: the Dutch, the German, and the Belgian people, and we're gonna have a covariate and that covariate is random normal distributed for 20 people with a mu of 8 and a sigma of 1. And we're going to create some dummy variables because we have categorical values in our model. And the way this works, if you apply a regression model, is that the dummy variables essentially states if your category is on or off in your regression model. It means that if you spell out the complete regression model, you can actually see when one of the categories is turned on or off. So dummy variable 1. So let's assume again for a second that category 1 is Dutch, 2 is German, 3 is Belgian. I'm going to have to remember that. Dutch, German, Belgium. So I've created categories, groups with values 1, 2, and 3. And this first dummy variable 1, states that if the group number is 2, so that means if you are, I forgot.
German.
Yeah, German, thank you. If you are German, then the dummy variable is set to 1. And in all other cases, it's set to 0. So that means you have a column in SPSS that is only 1 if you're German and 0 in all other cases. And dummy variable 2 states that if your group value is 3, so that's Belgium, then it's set to 1, and in all other cases it's set to 0. Got it?
Yes.
Yes.
Cool. Now that we have our dummy variable, we can determine, or I'm simulating the beta coefficients for our regression model. So I have the intercept B0, where I set my value to be 15. It's totally arbitrary, but it's a value of 15. And the B1 is 3, B2 is 4, and the B3 is 3. So the B1 and B2 relate to the dummy variables, the two that I have, and the B3 relates to the, let's call it the weight of the covariate. And I add some error to the term. Now, if I apply such a regression model, and I'm going back again to how field defines always on, I think, every page of the book, how the outcome is the model plus the error. That same holds for the covariant analysis. So if the outcome is the model plus the error, the model is defined by the independent variable plus the covariate. So it's essentially the nationality that you have plus the openness to experience. Now, if you want to formalize that, and I'll go into the question that I saw come by in the chat, the formal model for that is a regression where you define first your intercept, then a beta coefficient dummy variable 1 plus the beta coefficient of the, for dummy variable 2 plus your beta coefficient 3 times your covariate. So where you would when you actually run a covariance analysis or a regression model in this sense, a regression analysis provides the estimation of your beta coefficients, but in this case we're putting them in because I'm simulating the data. So if I'm simulating this data, going up one slide, I've chosen some arbitrary values of the the beta coefficients, 15, 3, 4, and 3. I have specified my dummy variables that either turn your beta coefficient 1 or 2 on or off. And that means that I actually have all the components to simulate my outcome variable. And that's what I'm doing here. So what I'm stating here is that my outcome variable, this one, is the result of my beta coefficient 0 plus b1 times my dummy variable. So we'll go into the example in a second. And we have to add the beta coefficient of 2 plus the dummy variable plus the weight of the covariate. And finally, we add some error to the term, to the complete model to add some randomness to this whole thing. Now, if we apply this, then we can see what happens here. So we have people that are in group 3, group 2 or 1. And we've defined our dummy variable. So let's first look at someone that's in group 1. So this is a German, Dutch person. Very good. Okay. So what we're stating is that our regression model states that if I want to, as I'm simulating these results, my beta coefficient for the intercept is 15. Okay. My beta coefficient for the first dummy variable is also 3, but I have to multiply it with 0. So as we look here, my beta coefficient 1 is multiplied by beta coefficient by the dummy variable for 1. So if I am looking at this person, the dummy variable states, what does the dummy variable say here? What does it state?
There is no difference between the groups.
Sorry?
There is no difference between the groups.
Not really. So the question is more about what is the meaning of the fact that this is a 0 for this dummy variable?
That is
we're looking at group 1.
German.
That's two together. One go first. Go ahead.
Because we're looking at group 1, and the dummy variable was always 0, only if it was
Exactly.
not group 2.
Exactly. So what it's saying that this is not a German person. Very
There
good.
were questions in the chat.
Mhm.
What exactly a dummy variable is?
It's essentially turning a beta coefficient on or off. So it's a dummy variable that just says, well, if you're German, then you're a 1. And if you're not, then you're a 0. So it essentially turns on one of the categories within your regression model. So because it's now turned off, because we know this is a person in group 1, so it's a Dutch person, so its value for the Dutch person for extroversion is 15. And because it's not a German person, the dummy variable is 0, is turned off. So I multiply the 3 with 0. So your whole term, the 3 goes away, right? Because you multiply it with 0. So that term is gone. So we're still at our expected value for our Dutch person to be 15. Now, the second dummy variable, what does that state? In the same line of reasoning that we had a second ago?
But they are Belgian.
That they are yes, and the fact that it's 0 means that it's not a Belgian, because we know it's a German person. So it turns off the second beta coefficient. So the second beta coefficient was 4, and we have to multiply it with 0, so that's also 0. So our expected value for our Dutch person is still 15. Now we have to add the beta coefficient for the covariate? Well, the covariance is a continuous variable, so we add that covariate to the model. And we have some error left that we also added to the model, which if we then for this person add up the whole regression model, we have 15 plus 3 times 8.42 plus some error of minus 45, which will land us an expected value for this person of 39.81. So the dummy variables essentially turn off the categories. So if we have someone in group 3, then we would have the beta coefficient of 0 would be still 15, but this is a Belgian person, so it's not a German person, so the beta coefficient for 3 is turned off. It is a Belgian person, so we add the beta coefficient for the Belgian people. And we add the covariate, and we add the error, and that means that we can determine the expected value. So we can determine the value that we have for this person. Going this route, you should realize then that what are the expected values if you do not take into consideration the covariate and the error here. So essentially you would think that a Dutch person, if you don't take the error and the covariate into consideration, would score 15 on extroversion, and a Belgian person would score 15. Belgian person should score 15 plus 4, so that's 19, and a German person should score 15 plus 3. So that are the group variables that we essentially have here. So if I simulate this data, and of course this doesn't happen in real life, but I wanted to make it a little bit explicit, because if we actually look at the means that we put into the model, essentially, then we have to see if that comes out again, if we run our analysis or not. So the question in the chat is that the means in the difference in the means in the groups? Yes, that is. So if you're looking at this one, you're actually stating that if you're a Dutch person, then your expected score is then your actual mean that we have within that group is 15. If you're a German person, then what is that? What is the mean that we put into our simulation for the German people?
3.
18.
18.
Exactly. So it because the regression model adds it all up, it's 15 plus that 3. And that also means that for the Belgian people, you have to add 15 plus 4. So the actual means that we put into our simulation, and where the means for these specific groups that we've put in there are 15, 18, and 19. Does that make sense?
Yeah.
Okay.
It does. And should there be assumption about equal variances between those covariates as well? Or is that something we don't take into consideration?
I'm not modeling it here. Actually, I'm because I have the. No, I'm not modeling that in here at this point. So, and the equality of variance within the covariate is not particularly relevant. The equality of variance on the dependent variable is. Okay, so we applied our regression model we've simulated some data, but this is not the data that you're gonna see if you actually gather your data in a real life experiment. What you're gonna see is something like this, where you have a group variable, either Dutch, German, or Belgium. You have a covariate that you apply, openness to experience in this case, and we have some outcome variable in this case. It's extroversion, and we have the scores on those essentially 3 columns, and you apply your ANCOVA on the whole model. So if we just look at the outcome here, we look at the outcome value, and we see we have all these scores that are in there, and we would say, well, okay, I see I've done my experiment. I've gathered all the data on how extroverted the Dutch people and the German and the Belgians are. What are the means within these groups? So if I just look at that outcome value and calculate the means, I see that the mean score for the Dutch are 38.67, for the German are 42, and for the Belgians they are 43. And this is what you would get out of your data.
Is openness to experience or extroversion?
It's on the outcome variable. So we
extroversion.
want to have, and our outcome variable was extroversion. Did I say that incorrectly? I meant.
No, that's correct.
Okay. So what you're seeing here is the means in these 3 groups are totally not the means that we've actually put in the model, because we put in 15, 18, and 19 as our means for our 3 groups. So what you're actually seeing here is the interference of our covariate in the actual scoring of that we're having here, and we want to try to separate these two, get the covariate out of there, and look only at try to get a notion of only the results for the groups that we have. So if we just run a regular regression analysis, or at least one where you only have the predictor variable in it, you would get a beta coefficient of 38 for the intercept, and 3 and 5 for factor 3. So what this means is that if you don't take the covariate into consideration, so you only analyze your data based on the grouping variable and your outcome variable, the beta coefficients that you get, and in other terms the means within these groups, are not reflecting the means that we actually put in there, and are not reflecting the beta coefficients that we actually put in there, because it's too high. This is not 15 for the intercept, and this is not 3 as we put in there for the B0, and this is not 4 that we had put in there for the second dummy variable. So you see that our view on what's actually going on is getting skewed by the fact that we're not also adding our covariate in here. We could also look at what would happen if we only look at the analysis with the covariate as a predictor, and just don't take the grouping variable, the independent variable, into consideration. And if we do that, we get, of course, again an intercept and the beta coefficient for only the covariate, and this also doesn't reflect what we actually put in there, because we've simulated the complete model, where we have one model where the covariance is in there and also the beta coefficients are in there. So what we actually need to do is run the regression analysis with the complete model. And the complete model is, of course, adding the grouping variable, the independent variable, and the covariate as a predictor. So that's what I'm doing here. In the top row, I'm running a regression analysis in R, where I'm predicting the outcome based on the grouping variable, nationality, and our covariate, the openness to experience. And what we get back here is then an estimation of the beta coefficients for this model. And when we do this, we do the complete model, then we see that the beta coefficients that we put in there actually represent the beta coefficients that we expect when running this model actually come close to what we actually had put in there. Why isn't this exactly what we put in there? Why isn't this exactly 15? And why isn't this exactly 3 and this exactly 4? Anyone? Yeah? You may also say it, right? Just turn on your mic and say, well, it's the error. Yes, it's the error. We also put error in our model because otherwise we would always have a perfect model, and in our simulation we actually added an error term. So that means that the beta coefficients that the regression model, essentially the covariance analysis, recovers are actually the things that we put in here. And if we add the intercept plus the beta coefficient for the first dummy variable, that would mean being German, then we have the mean for the German group. And for the second dummy variable, that means being Belgian, that would mean that our mean for the Belgian people would be about 19, and it's a bit higher here because we have this error term. So I just added them up, and then we can see what are the means for the Dutch, what are the means for the Germans, and what are the means for the Belgian people. And actually this is what we had put into the model. Does that make sense?
Yes.
Yeah. So these are some hard steps, and Field explains them also thoroughly. With so also look into that. But I want you to have a notion that the most important part for me here for you to understand is that having a covariate influence your outcome actually clouds the actual scoring that you have, and if you correct for that, then you can recover the actual values that the group means would be, in essence. Okay, so this means that if we're making the step to explaining variance again, because now we know what the covariate does, why we need to apply it to recover the actual means of the groups. But when you're doing analysis of variance, and also when you're doing analysis of covariance, you're analyzing the variance components that we have again. So that means, in the same line of reasoning that we had last week, we need to dissect the variance components that we have. So the first question, of course, again, is how much variance is there in this data set? So in other words, we have our scores of extroversion, our extroversion scores, and how much variance is in there. So the answer to this question is just applying the variance function in R to that variable, and then you know how much variance there is. So applying this variance function will yield you 11.9 as the average dispersion within these groups. So if we want to get to the, if we want to decompose that average dispersion into what is then the sum of the dispersion, or in other words, the sums of the squares, then we can multiply the variance again by the degrees of freedoms. That's n minus 1. And that would yield us 227.5737 variance units. And then you're again like, what are you talking about? And that means that to get a notion of what this means again is going back again to understanding the definition of variance, meaning the difference between the total between the mean of the group of, in this case, our outcome variable extroversion, and the actual scores that we found. So the difference between the grand mean. So for this entire column, the outcome column, if I calculate the mean for that entire column, that's 41.3505. And if I look at the difference for this individual between these two scores, that is a variance component for that individual. And we do that for all these people. So if you square that distance and add those squared deviations, then you're back with your sums of squares again. But let's visualize this again. So we've done this before, where we've seen the individual people on the x-axis, and the dependent variable, the outcome, in this case extroversion score, on the y-axis. You have the scores of the individual people here as the small dots, and the total group mean we see as a horizontal line. So what we're trying to explain, again, just like last week, is the deviation from that mean. So this vertical line again for each of those individuals, can they be decomposed again into an explained part and into an unexplained part? And that is the thing that we're trying to discover, is if we can determine an explained part, then we can set that, we can weigh it with the unexplained part, and we are back with our signal to noise ratio. We're back at our F value again. So this is the total amount of variance that can be explained, that there is to be explained. Does that make sense?
Yes.
Cool. Okay. So we're going to try to dissect the explained variance part into a few steps. The first step is we're going to disregard the covariance, and we're only going to look at the grouping variable. So essentially we are creating a model for the variance within the groups. So that actually means that this is the same approach that we applied with the with our one-way ANOVA last week. We're just looking at each individual in the group that it's in. So this person is in group 1, this person 2. So we're going to ask ourselves the question again, what is the mean of that group? And we set the group mean, so the expected value for that individual, to be the group mean. And we do that for all the people in group 1, and we do it for the people in group 2 and group 3. So for the Dutch, the German, and the Belgians. And we see the group means here again for each group. So explaining this part, explaining the variance for only the grouping variable, would is in the same line of reasoning that we have for the for the one-way independent ANOVA. So we just have expected values here. So all these people are in the same group. We expect their scores to be here, and that also holds for the German people, and it also holds for the Belgian people. So the explained part for the group model is the distance between the total mean and the group mean. And if we square the distance, the red vertical lines here, and add them all together, and do the same for the green ones and for the blue ones, for the Germans and for the Belgians, then we have our sums of squares for our group. Does that make sense?
Yes.
Okay. But now we also have our covariates. So what we're going to do is we also want to look at a model with only the explained variance of the covariate. And because our covariate is a continuous variable, it's not a grouping variable, we can apply a regression model and see what the expected value is within that model if we only apply the covariate. So in this case, we see, well, calculating or the expected outcome, calculating the expected extroversion level based on openness to experience, and because it's a continuous value, the covariate means that all expectations for each individual can differ because it's a continuous variable. So for the first person here, the model based on the covariate expects extroversion level of, well, say 44, what is it, 42 or something, but it's the actual score on extroversion for this person is much lower, so it's off a bit. But the explained part is this one. And for this one, the explained part based only on the covariate would expect the extroversion level to be 40, but it's actually a little below 36. So the explained part based on the covariate again is the red vertical line. So if we want to know what the sums of squares only for a model where we apply the covariates are, then we have to square the distance for the expected values here. Add those all up for the Dutch people, for the German people, and also for the Belgian people, and then we have our sum of squares for a model where we only apply the covariates. Does that make sense? Still? Yeah? Very good.
It makes sense, but it's a bit harder to grasp for me.
Yeah, of course. Yeah, because if you're looking at this one, you're seeing, well, we have the means of the group, so the expected value is totally clear because I can see the means. But for the covariates, it's applying essentially a simple regression analysis with one predictor variable and one outcome variable, which gets an expected value for the outcome. But it varies per person. So the next step that we need to do is, and we've seen this, of course, that if we apply a model where we calculate an expected extroversion level based on both the grouping variable and the covariate, both the nationality and the openness to experience, then you would combine these two. So in one model that we've seen, we only had the grouping variable, so the expected value for each individual was just the group mean. We've seen it separately for the covariate, and we've seen that because it's a continuous variable, it can differ for each individual. So if you combine these, it will also differ for each individual, right? Because it's a combination of the grouping. It's a combination of the grouping variable, where you think that it's only the group mean that is the explained part, and you combine it with the continuous variable of the covariate, which can be different for each individual. So if you combine these two, you could have an expected value. Let's see. You can have an expected value for each individual based on both. So let's look at this visually. And this means the following. So what we're seeing here is when you calculate an actual expected value for each individual based on the grouping variable and the covariate, you will see individual differences about the expected values. And that those expected values are based on both the grouping, the knowledge, the information that is in there of being part of the group, and the information that is in there for the covariate. So we see for this person, we expect now, because we're also adding our covariate, to be, well, a little bit above 40, and its actual value is a little bit below 40. And for this one, we think it's 43 or something, maybe a bit lower, but it's a bit higher. So these are all our expected values. So what we're seeing, at least, if we look at only our covariate, well, we have a few good shots, but we have some that are really off. If we only look at our grouping variable, we also see that we have a few good shots, but, well, there are also a lot that are totally the wrong direction. But combining these into a model where we also add the covariate, now we have a complete model, which, well, if we look at this, well, this is a pretty darn good model. You have a lot of explained variance. All the expected values are actually quite close to the actual scores that we found. So combining these two, the covariate and the independent variable, well, if I look at this, it makes for a better model. Won't you agree?
Yes.
Yeah. And so, in essence, that is what you're doing with adding more predictors to your model. You're trying to get a better fit of the model. And what you're seeing here is that in this model, you actually are reducing the amount of error that you have, because, yeah, the covariate adds to the explanation. So when you're determining the error term, so the way the amount that you're actually off, the residuals, the sums of squares of the error, the mean squares of the error, the variance of the error, you're using the information of the complete model. So if we're looking at the error variance, of the model where you combine the covariates and where you combine the covariate with the grouping variable, then the purple parts are the error, and that's the difference between what the model expects and the actual scores. So we've reduced the amount of error that we have by combining these two. We see that, and I haven't added the error term here, but you can see that well, the error terms will be bigger because we have some that are really off or even to the other side, and that also holds for when you only look at the grouping variable here. We have the amount of error would be insane here. So so by combining these two, we're actually reducing the amount of error. Okay, I absolutely need coffee. You too? We'll stop. We'll continue a quarter past. See you in a bit. I'm back. We're continuing with coffee this time. Oh, this does so much good. You walk into the kitchen and you smell the coffee, and on such a miserable day. Well, okay, here we go. So we've seen that we reduce the amount of error that we have by combining the predictor variable and the covariate. And we have to do a final step because we're actually saying that we want to know the amount of explained variance for we actually want to know the amount of explained variance for the group variable if we correct for the covariate. So in the final step, what we'll be doing here is actually calculating the sums of squares, but for a few things. So first off, we have the sums of squares for the model, and with the model, I mean the total model. So the model where we combine the covariate and the grouping variable. So that's this one. So if we're looking at sums of squares, and the explained variance, we're talking about the distance between the total mean and the expected value for the individual. So all the red vertical lines squared, added up, and this also for the German and the Belgian groups. So determining the amount of sums of squares that we have for the model. We're also determining the amount of sums of squares for the error, so that those are all the purple vertical lines squared and added. And finally, we also need to determine what the amount of sums of squares are for essentially the models, and for two specific models, namely first the grouping, the one with only the groups, and only the one with the covariate. So the sums of squares here let me be explicit, for the group is how much variance is there if we're only looking at the groups. So that is this one. All these distances here, all the vertical colored lines squared and added. And the second one is all these vertical lines squared and added. So these are the ones for the covariate. So what we do in the final step here is that if we actually want to know what the sums of squares for the covariates are corrected for the grouping variable, we do that by stating, well, we know how much variance there is in the combined model, and we know how much variance there was explained in only the model with the group. So if I subtract the amount of variance that I have only in the groups from the combined model, I'm actually left with the part of the covariate that's corrected for the grouping. Now, mostly we're not interested in this, we're interested in the opposite. We're interested in the groups corrected for the covariate. And that goes by the same principle. So we have the sums of squares for the model, the total combined, how much explained variance is there if we put both these predictor variables, both the predictor variable and the covariate in there. And if we then subtract only the explained variance from the covariate, then what are we left with? And that is the sums of squares for the groups corrected for the covariate. Does that make sense?
Yes.
And I read in the chat that you're scratching your head at this point. And of course, I get it. It's hard stuff. This is the first time you're hearing it. You have to combine this with reading the book, with diving in, with doing some calculations to make it your own. I understand that if it would be clear from the first run that I explained this, then we wouldn't even have to provide exercises, and then it would be done. But it takes effort and it takes practice to really understand these notions. So don't worry if you're like, how exactly? This is only part of the total picture. So it's reading the book, it's viewing these lectures, it's making the assignments. All this will hopefully accumulate into you at one point actually fundamentally understanding the notions that we're talking about here, right? Okay.
There's a question in the chat about how and to which extent you have to be able to do this yourself in R, or whether the Kickstarter will be supplied again.
Yeah, I understand. So if you read field, then you see that at some points he skips the calculations because it gets too difficult. So if you're looking at my slides, for example, this one, well, I calculated the grand mean and I subtracted it from the model expectations, but I never explicitly stated how we get to the model expectations. So I'm not expecting you to do so either. So this is conceptual understanding what is going on, trying to visualize it for you. If you see that field in his chapter doesn't even provide formulas for calculating these things, well, then you sure as hell don't have to do it for me in the exam. So you have to be able to understand these conceptual parts. So the thing that I'm showing here, for example, this is relevant, right? So it's relevant to understand that if you want to look at how much variance is explained when correcting for the covariate, then it's a conceptual, you have to have the conceptual notion of, okay, if I have a model which combines them, then it explains this much. And if I then only have the thing that is explained by the covariate and I subtract that, then I'm left with what is explained uniquely by the independent variable. So those are conceptual steps that you have to make. So there are no formulas here, so I won't expect you to do any of those. Does that make sense? That does make sense, right? I hope. Okay, so let's see. So in the final step, and this is important to notice, because what we're stating here is that, well, the sums of squares for the groups are actually corrected for the covariate. So we now have our sums of squares for the groups that are corrected. But we have to transform this into an F value. So we have to have a notion of the signal to noise ratio. And the way it's done is by calculating the mean squares for this specific model, and calculating the mean squares of the error for this specific model, and maybe I could be more explicit, but what I mean with this model is the sums of squares for the group corrected for the covariance. So to get to the mean squares, you have to divide the amount of sums of squares that we've corrected for by the degrees of freedom of the model, which is stated here. It's the k minus 1, where the degrees of freedom for the error, we also need that for the mean squares of the error. But the thing to notice here is that the error term is determined by the full model. So we're going to see this again tomorrow in the factorial ANOVA. The moment you start adding predictor variables and you are expanding your predictive model, your error term, if your error term shrinks, you're using the error term of the total model. So you calculate the error term based on the complete model, and then you can look at the different parts, but the error term always stays the same, stays based on the total model. So therefore, when adding a covariate, you're actually decreasing the amount of error that you have in your model. So that is essentially what you're applying here. You're stating, well, I have the mean squares of the model, I have the mean squares of the error again, so I have a signal to noise ratio, which leads me to an F value of 21. Do you think that an F value of 21 is significant? So you can also digitally say yes in the in Zoom if you want. Sorry?
Yeah, it's significant.
Is there anyone that doesn't agree? And the other question, of course, is there anyone who doesn't know? Is not sure? Yeah. Very good. It's lots more.
I'm not sure.
Okay, so
Sorry.
no problem. So the F value is a signal to noise ratio. So we're stating that if there's more signal than noise, then it can be significant. So if there's equal amounts of signal to noise, because it's a ratio, it's a division, you're getting values close to 1, right? If there's just the same signal as there is noise, then your numerator and your denominator are essentially the same. But if your amount of signal increases, then you get bigger values, so you have less noise. So logically that follows that if you have very high F values, that means you have a lot of signal. And trying to relate that to the null hypothesis testing, then we have to think about, well, what does that mean in terms of what you would expect if the null would be true? Well, if the null would be true, then I would not expect a lot of signal. If the null would be true, I would expect the same amount or even less, because we assume there's nothing going on. So under the assumption, as we've seen last week, such a distribution, I'm showing it here, but it's not very pretty. I'm gonna show a prettier one. But under the assumption of the null being true, we can plot an F distribution, and we will see that the most prevalent, the most frequent observations of F values, if the null is true, given this sample size and the amount of groups that we have in here, small values of the F are more prevalent than large values of the F value. So having an F value of 21 Well, it's quite large. But quite large, of course, then you have to be able to relate the amount of the height of the f value to the distribution. So if we look at this f distribution, for example, which is so based on degrees of freedom of 2 and 16, you see that it goes down quite rapidly, and even at the number of 2, an f value of 2, this is quite infrequent if the null were to be true. So what it's stating here, that the probability of an f value larger or equal to 21.7 is equal to 0.00000027. So this is highly significant. The f value, it's off the charts, and I think from where I live, I think it's actually at the UvA. So it's so you have to try to get a grip on the height of the test statistics and how they relate to such a null distribution. So for example, if I show you this one, so this is the same null distribution. So this one is the null distribution of the f value, and you see that if you look at those scales, well, it's obvious to see that a value of 21 for an f value is quite unlikely, right? You see that? Do you?
Yes. Yes.
Okay. So looking at such graphs and just looking at how those scales are at the x-axis gives you a bit of a notion on when you're willing to put your hand in the fire to say yes, it's significant or not. Because if someone tells me, well, I've got an f value of 10, then I will say, well, then it's a significant f value, and I'm willing to bet a lot on it. Because you see how the shape of the distribution is, and well, it doesn't vary a lot if the null is true.
Can I ask you from which f value you'd be able, or you'd be willing to put a lot of money in?
Yeah. So of course it's based on the shape of your distribution, which is determined by the amount of degrees of freedoms of the error and the model. But I think if you look at the lecture slides from last week, I've plotted f distribution where the null is true with varying amounts of degrees of freedom, and you see that almost always at 5, 6, it's down at the bottom again. So if it's above 6, then it's probably significant. It's very unlikely. You have to have a very strange model, in the sense that you have to have a lot of participants and small group sizes to even be able to have significant differences. So something around there. So what are we seeing in this graph? Anyone? I'm reading alpha and power, type 1 error in red. So alpha and type 1 error are the same, right? And it's in red. That's someone who agrees? Give me a yes in the chat, or the well, just hit the yes button in Zoom. Who agrees? Alpha in red. Yes. And the power is then in green, right? Agree? Cool. So what do we call what do we call this f value? So we have on the x-axis the f value.
Is that critical
And
value?
this one is the critical value. Yeah. So based on choosing an alpha, choosing a type 1 error, and it could be 5%, and in this case it is, but you don't have to, right? Based on an type 1 error of 5%, you determine, or SPSS determines for you, or I showed here to you what the area under the null distribution is that is associated with an area of 5%. And the cutoff score, the critical points that is associated with that area, that is what we call the critical area. And what are our conclusions based on this critical value? And even if you don't want to say the answer, it is important to think about what the answer should be, right? What are our conclusions here? We have two.
That there is a difference between the groups when corrected for openness to experience.
Exactly. And on what, based on this graph, on what side are you concluding what?
Well, you've got the f value, which is far beyond the critical value. So therefore, given that the null hypothesis is true, you could definitely assume that your conclusion is statistically significant.
Yeah. And so bringing it back to the critical value, on the right side of this critical value, you're rejecting the null, and on the left side of the critical value, you're not rejecting the null. So if you find, based on your data, some f value that is on the right side of that critical value, then you reject. And then we have to look again back at the Neyman-Pearson null hypothesis testing paradigm, because if that is your critical value and you have your decision based on that one. Now, if we assume this alternative distribution to be true, and with alternative distribution I mean this one. So this is some arbitrary alternative distribution of f values where we do assume a high signal to noise ratio. So such an f value could look like this. Then concluding to reject the null also is associated to, well, the probability of some other, and let's for example take this one, alternative distribution to be true. So what do you think that the probability of the alternative distribution to be true is?
Would that be 1 minus beta?
Yeah, it's sure 1 minus beta, right? Absolutely. So, but what is 1 minus beta again? What's it called again?
Power?
Exactly. So the probability of correctly refuting the null is the definition of the power, right? It's a good decision. If this other distribution would be true, then that would be a good decision. But I'd also like to know what the amount of what the height is of the probability of this decision. So what I'm seeing here is a very huge area, a very huge green area, So based on this graph, I would think that our power would be, I think, close to 80% something. I'm not sure, but it's high because you see that it's a lot of area under this curve. So the probability that you're making a correct decision, if this alternative distribution would have been true, is high here. So that is what we're seeing. So you have to relate your knowledge of the null hypothesis testing, the things we covered in the first block, to what that means in this block for the F distribution. And the concept is still very much the same. It's you make a decision on that side, you reject to reject. On the other side, you decide not to reject. And how does that relate to the power and of your test? Okay, very good. Let's have a look for a second before we stop at what this looks like in SPSS. So we're going to switch to SPSS now. Here we are, and I've got the same data as we have in the slides as we calculated for our analysis in SPSS here. So I'm gonna ask you to run me through this, because if I would want to do the covariance analysis, I have to check the assumption of the fact that the values of the covariate should not differ between the groups. So what do I have to do first? Here.
ANCOVA.
Okay, so I go to analysis and then
Compare means one way ANCOVA on the bottom.
very good. Yeah, and then someone else can chip in, right?
I think covariate goes to the dependent list.
Could you repeat that for me?
I think covariate goes to the dependent list.
Very good. Yes. So, and the independent, the factor list.
Factor
Group.
list.
Yeah. Very good. So what we're essentially saying here is we want to know if there's a difference in the means for the three groups that we have on the covariate. Well, we don't need to. We're not actually interested in what those differences are, so we're not doing post hoc analysis or contrasts or anything. We just want to confirm our assumption, and if that's confirmed, then we can go on for the rest of our analysis. So what do we conclude here?
I'm sorry, I just have a question. I thought we were testing for the covariate, but now we added the outcome to the dependent list.
Yeah,
Did I make a mistake?
yeah, I think so.
Oh no. Again. Oh yeah, you're right. I clicked the wrong one. Okay. So, very good. Keep me sharp. That's so what are we concluding here?
That there's no significant difference between the covariate across the conditions.
Exactly, and that was one of our assumptions. So we're done. This is good. One assumption checked. What's next?
Run the analysis of the ANCOVA.
We could run the analysis of the ANCOVA, right? But we also want to check the assumption of the regression slopes, right?
Yeah, right.
So what could we do for this? We want to know if the regression slopes are equal across the three groups. So in other words, what is the relation of the covariate with the dependent variable for each individual group? So what could
Can you
we
use chart builder for this?
Yeah, we could. Let's see how far we get. We can go to the chart builder. Just you say it and okay. Don't show this again. Oh. Here we are. Chart builder. What now?
I'd say a line graph.
A line graph? If anyone
then
doesn't agree, you can just shout it out, right?
You would have to use a scatter plot.
Scatter plot.
You think a
yeah.
scatter? Yeah, that's true, because we want to have the relation between covariate, which is a continuous variable, and the outcome variable. So the scatter plot would be, I think, the right one to do. So am I doing the scatter plot right? Let's see. So which one would I choose?
First one?
Do the first. Oh, sorry, I misclicked. The first one. So. Okay. And now,
And,
so
the group on the x-axis and covariate on the y-axis.
yeah, so I have to want to see the relation between the outcome variable and the covariate, and I want to have what now? Am I done or not?
Filter for group.
Filter for group. So I have to use the grouping variable and have to filter for group. Let's see if that works. Filter doesn't show up, but I can put it here. Does this work? No, this is not nice. This one? Yeah, different colors. Looks pretty, right? Let's see how far we go. So if we run this, we will get this. And well, I'm interested in the regression slopes. So this is a hard one, right? Because now I have to eyeball this to see if there are if the regression slopes are actually equal for these. And that's hard to do. So what I can do is double click the plot, which will open the chart editor. And if I click the dots, I think I can use the option. Which one is it again? I think this one. Slopes for, yeah, here we go. So this is the regression lines for the different groups, and now it's visualized inside the plot that we created. And now I can see, well, this looks quite the same. So it's so what it's showing you here is the relation between the covariate and the outcome variable for each individual group. We have the regression line, so we can visualize this too. So this is a good approach. What could we do more? Because the thing is, right, because, well, now, do we determine that for example, group 3, the Belgians, it's not really the same as 1 and 2. So is this a problem or not? So what can we do to determine this?
Could we do an ANOVA on the regression coefficients to compare the 3 to each other?
That's a good idea. So you would actually see if the beta coefficients would be equal. I don't think the ANOVA can do that exactly, because the ANOVA needs a vector of scores to actually perform it. And what you're suggesting is that you actually compare the beta coefficients. But the thing to realize here is that what we're looking here at here is actually an interaction. So if these lines are straight, then there's no interaction. But if it's the other way around, there is actually an interaction going on. So we could test this by performing an ANCOVA with the interaction term added. And we can do that by changing the ANCOVA model in SPSS and just looking if the interaction term is significant. So this is actually the one time in this course where we in SPSS change the model as it is determined in SPSS. We're going to do a general linear model univariate, where we determine use the outcome variable as the dependent variable, use the grouping variable as the fixed factor, add the covariate. And if I would run this analysis now, then it would just be a plain old simple, no, well, not simple, but it would be the covariate analysis as we want it. But we are not interested at this point at the analysis of the covariance. We're interested in this specific assumption. So what we have to do is change the model here. And we're going to build our own, where we add the grouping variable, we add the covariate, and we add the interaction of both. So we're expanding our model to not just have the predictor variable and the covariate, but we're also adding the interaction term to this. And this is what we're interested in, because if this one is significant, then we have a violation of the assumption. So we're going to run this analysis, which actually runs the ANCOVA, but this time with, let's see, with the interaction term. Oh, where are we? Yeah, I'm having my zoom is not zooming at the right point I'm seeing here. So we now have the interaction term added, and we see that this one is not significant. So now we know, we tested if this slight interaction that we're seeing, the fact that this one is a bit steeper than the Germans and the Dutch, we have tested this for significance, looked at the interaction term, and it's not. So our assumptions are now met. And this means that we can actually perform the ANCOVA as we want to. Means that the settings are essentially the same. The only thing we have to change is the model. We have to put it, turn it back into a full factorial model without the interaction term. So if we, so now we are interested in the actual results. So that means that we could look at the contrasts. So if the ANOVA states that there is a difference, then we're actually interested in to find out where those differences are. So we could look at one of the contrasts options, and we have a lot in SPSS. And I for this course I won't ask you to know which one is what. The one thing I do want you to know is that the Helmert contrast is essentially the most strict, and therefore, well, I dare to say it's the only contrast that is that really respects the fact that you have a limited units of variance to explain. So that means that if you're peeling apart the contrast, the components of the variance, you can't compare groups multiple times, and this Helmert contrast does this. So it in essence is the best contrast, but it doesn't always give you answers that you want to see, because if you can't compare all the groups, then sometimes you have a hypothesis which do need multiple comparisons. So for example, if your hypothesis is that your your new treatment works better than the old treatment compared to the baseline, then that means that you would want to compare the baseline to the new treatment and compare the baseline to the old treatment. And well, the Helmert contrast cannot give you an answer on that. But we'll go on into go into the contrast more later on in this course. We could create some plots, and we don't have post hoc tests enabled here. So if you look at the button, it's grayed out, but there is a way to get some post hoc information. Sorry, not options. It's under estimated means. So here you have the option to assign for the group variable that you want to compare the means. So you have an option here that says compare means. And if you look at these, well, we actually have post hoc tests available here. So you can get to the post hoc tests if you don't have any hypothesis. Well, we'll look at some options here. Some of the descriptive statistics. We do want to check for equality of variance. So we do the homogeneity test of equality of variance here. And for now, we'll leave it at this. Continue. And run the analysis. Now, one thing that sometimes goes, I see go wrong with students and sometimes also at exams is that now I've run multiple analysis in the output of SPSS. I have the ANOVA here, ANCOVA results here, but this one was the one with the interaction. And now we've run another ANCOVA, but without the interaction. And that sometimes people look in the wrong table for reporting their results. So you have to realize that if you're doing the ANCOVA, then you have to look at, the newly created analysis without your interaction term. So, what we're looking at now is the table for the ANOVA, for the ANCOVA, where we see the we see the sums of squares for the covariate, for the groups, for the error, for the total, and the thing that we're interested in is what are the group, what is the sums of squares for the groups, because we want to know what is the effect of group corrected for the covariate. And this value that SPSS just gives you of 54, this is the value that we actually calculated within our when we actually looked at the sums of squares. So what SPSS is giving you is the sums of squares for the groups, and that one was based on the amount of sums of squares that you have for the combined model minus only looking at the covariate. That's this one. So we've gone through all the steps. We've seen how we get to the sums of squares, how to get to the variance components when we correct for the covariate. And that is what SPSS is giving us back, exactly the same value. So that's reassuring to see that the steps that we've taken are actually the step that that SPSS behind the scenes takes for you. And what we've also seen in those slides is that the error term here is determined by the complete model, and this is also the same as we've calculated. We've looked at the purple vertical lines that we've created on the total on the combined model, and that is actually the error term that we'll be using. So what we're seeing here for groups is that we can calculate the mean squares. It's dividing by the degrees of freedom. And for the error, we can also calculate the mean squares for the error, also dividing by the degrees of freedom. So we have the mean square for the model, the group model. We have the mean square for the error. So in essence, we have the signal and we have the noise. So if we divide these two, we get to our F value of 21.709. And SPSS also gives you in the final step back the significance level of this, the p-value of this F value.
I'm sorry, one question. What's the sum of squares for the intercept? Where does that number come from?
Yeah, it's only looking if you look at the intercept as an expected value, you can also calculate sums of squares for that part, but that's totally not interesting and relevant for the questions that we have. So I've left that out in our calculations, because what we're interested in is group differences, and the intercept, as you've seen with the model that I create, the simulation that I've created, my intercept was 15. Do you remember?
Yes.
So it's only a value that is used for determining if all other predictor variables are 0. What is the height of the, where does it cut the y-axis? So, and in this case, related to our example, it's the value of our dependent variable of not openness to experience but extroversion of the Dutch people. So it only represents then one group, and that's not relevant for this design. Okay.
Yes, thank you.
So finally, and then we will quit, is what we're seeing is we have asked for contrasts. So that means that we're doing the Helmert contrast, and the Helmert contrast splits like a tree structure apart the variance component. So what it's saying is we're comparing the Dutch people to the combined Belgian and German people, and that is not significant. So combining the German and the Belgian, they together do not differ from the Dutch. And in the second step, it compares the Belgians from the Germans. And sorry, that does differ. So I've interpreted this incorrectly. So the significance is lower, so it does differ. But for the and also for the difference between the Belgians and the Germans, we look at the significance level, and we find it here, and that also that is also significant, a significant difference. So you see the Helmert contrast goes in steps, and sometimes you don't want to have this this structure. Sometimes you just want to know, well, do the Germans differ from the Belgians, and do they also differ from the Dutch? So
could I just ask you on that, if the Dutch differ from the group Belgians and Germans, does that also mean that they differ from, is there a difference between the Dutch and the Belgians? And is there a difference between the Dutch and the Germans?
You don't know, because if you combine the two groups, they average out. So maybe your Germans are scoring quite high, and your Belgians are scoring quite low. And if you put those two together, then it averages out somewhere in the middle, and it could state that there, for example, is no difference between the Dutch and the combined groups, where in actuality there could be a difference between the Dutch and the Germans and the Dutch and the Belgians. So if you do it this way, it doesn't always give you the answers that you want.
But you're not allowed to reuse the Dutch group here.
No, exactly. So that means sometimes you have to violate this assumption to get to the answers, because otherwise you're not going to find it. And so one thing you could do is as a violation, of course, less strict, is look at the post hoc analysis as we've done here, where we just combine all the groups.
Can't see your slides.
Oh, sorry. Yeah. Where we just combine all the groups, so it's 1 versus 2, the Dutch versus the German, and that differs, and the Dutch versus the Belgium, and that differs, and the Belgium versus the Dutch, it differs, but the Belgians versus the Germans versus the Belgium, they don't differ. So this is what you find through your post hoc analysis. And you can choose for some correction levels on your post hoc analysis too, because you're doing multiple comparisons. The type 1 error rate could be inflated, so it could be not a very exact interpretation of what's actually the p-value supposed to be. But these are the trade-offs that we have to make. The other thing that you could do is plot the results and add the error bars. So you could also do that to see where the differences are, and that actually helps you to see the 95% confidence interval. So if they clearly are not overlapping, then you clearly see the differences. So it always helps to visualize also your results. Okay, I want to keep it at this. That was a lot, right? I'm stopping here, so I will stick around, so if there are any more questions, please ask them later on. Good luck with the weekly assignment again. We're going into this topic again in the weekly assignment, so it's coming back lots of time. So I'll think with the combined effort of reading the book, the lectures, and doing the assignments, it will eventually land. And well, seeing how good you've performed on the first interim exam as a group, I'm sure you will manage. So that is it for today. Thank you. See you tomorrow. See you tomorrow. Bye.
Thank you.
Bye-bye.
Bye.
Thanks.
Okay.